The first thing I want to talk about is the first four blue questions, or the bulleted questions for you, because it doesn't show the colors on there. Number one, it says, do you expect the mass of these cylinders to be the same? This is the three long, thin cylinders. Okay? So they want you to verify that they're 1 cubic centimeter. You did that. So we're going to say on blue question number one, yes, and the reason why, same volume and same substance. They have the same volume and they're made out of the same substance, so they should have the same mass. Number two then, well, 2, 3, and 4 are all dealing with this. It says suppose that the aluminum rod from which the three cylinders were made was cut into cylinders twice as long. So they were twice as long as they were here. What would be the mass of each cylinder? Well, we said the mass of the ones we had was 2.7. So we just take 2 times 2.7. It's approximately 2.7. You're going to get the mass of that one, which would be 5.4 grams. What would be the volume? Well, our volume was 1. So 2 times 1 is 2 cubic centimeters. And then number 4, how can you find the mass of 1 cubic centimeter of such a cylinder without cutting it in half? Well, an easy way to find the mass, if we knew that it was 2 cubic centimeters, is just divide it by 2. Okay, so if you just divide it by 2, you can find the mass of 1 cubic centimeter. Over to the next page. The first blue question on the second page, or blue question number 5, what's the mass of the short aluminum cylinder? It's about 2.7. It's going to be 2.7 something. Now, if you got 2.6, I'm not saying that's wrong, or 2.8, that's not wrong, okay? Because it may be. This is just what it should have been. And then it goes on to say, a piece of aluminum, a piece of brass, when you cut so they have the same mass or the same volume, can you make a piece of brass that will have both the same mass and the same volume as a piece of aluminum? That's no. You had a piece of brass and a piece of aluminum. They were both the same volume. But you notice that they had different masses. The mass of the piece of brass should have been about 8.5. To make them have the same mass, you'd have to cut some off of the brass one. They no longer have the same volume. Okay, so you're going to keep going back and forth, and you're never going to end up at a point where they have both the same mass and the same volume. It's impossible.
Is that number 6?
That's number 6.
Okay.
Yeah, so just put no for number 6. Then 2 and 3 are just multiple choice questions. Number 2, it says if the mass of the aluminum rod is 2.7, which of the following is the mass of the rod that would have a volume of 3 cubic centimeters? Well, it's going to be, the only one that shows a greater mass is letter C. So C is the only possible answer for that. And then number 3, if the mass of the brass cylinder is 8.5, which of the following is the mass of a brass cylinder with a volume of 0.6? Well, it's the only one that's going to be less. The only one that's less is letter A. I don't know why that won't right there, but it won't. So turn the page to the next section we did yesterday, which was density, dividing and multiplying measured numbers. And I want to take a few minutes and go over these questions. You were supposed to answer 4 through 8 and 10. So I'm going to move that up a little bit. Number 4, a parking lot's filled with automobiles. Does the number of wheels in the lot depend on the number of automobiles? If you look up the definition of automobiles, I heard a lot of discussion about this yesterday. Automobiles are 4-wheeled vehicles used for transportation. So let's just worry about it in terms of 4 wheels. Let's not worry about the spare tire or any other sort of automobile. So does the number of wheels depend on the number of automobiles? That's yes for letter A. The more automobiles you have, the more wheels. Letter B, does the number of wheels per automobile, which we said was 4, depend on the number of automobiles? That's no. No matter how many automobiles you have on the lot, the number of wheels per automobile is always 4. Okay, it doesn't matter. In order to be classified as an automobile, it has to have 4 wheels. And then letter C is the number of wheels per car or per automobile, a characteristic property of automobiles. That distinguishes them from other vehicles, excuse me. Yes. It doesn't distinguish them from everything, okay, but it would distinguish them from motorcycles, okay, or semis or something like that. but it wouldn't distinguish them from lawnmowers, okay, or a tractor or something like that. Number 5, draw a graph of the number of wheels in a parking lot as a function of the number of cars. So 5A, I'm just going to sketch a graph here. We'll put cars down at the bottom and then wheels here. And I'm going to say 1, 2, 3 cars, 4, 8, 12 wheels, and your graph is going to look like this. It's just going to be a straight line starting at 0. In other words, the more cars we have, the more wheels we have. It just continues to go up. Then on B, I want you to make another graph. It says draw a graph of the number of wheels per car as a function of the number of cars in the lot. Well, we said the wheels per car was always 4. So we'll say cars, wheels per car, 0, 1, 2, 3. But it's always going to be a straight line at 4. It doesn't matter how many cars you have. A characteristic property of cars is that they have 4 wheels. So even if you have 0 cars in the lot, they still have 4 wheels per car. And then number 6, suppose you plot the density of aluminum, which by the way is 2.7. The cylinders we had in the mass and volume lab they were 1 cubic centimeter. They had a mass of 2.7. And we're going to plot that as a function of the mass of several samples of aluminum. Describe the appearance of the resulting graph. Well, density of aluminum is just like the number of wheels per car. It's always 2.7. It doesn't matter how much aluminum you have, the density is always 2.7. So I'm just going to put on number 6. The graph would look like, it looks like 5B. So it's just going to be a flat line at 2.7. Even if you have 0 grams of aluminum, the density is still 2.7. So let's move over to the next set of questions, which was 7 and 8. I don't know if I need that over there or not. I'll leave those graphs up there for a few minutes in case you didn't get them in. And 7 and 8 both deal with significant digits, and so we're just counting the number of digits on 7, then we're doing a little bit of math on number 8. So 7 says how many significant digits are in each of the following measurements. So letter A, 4.0. That 0 is telling us it's measured to the 10th place. So letter A would be 2. That 0 counts. Remember, any number between 1 and 9 always counts. The question is whether the 0 counts or not.
What?
So on letter B, question?
What lesson are we on?
This is just number 7.
I know.
On
For mass and volume?
nope, the next section, which would be
Density?
this. Density and dividing and multiplying measured numbers.
Oh.
Should be the section after mass and volume.
I think I did the wrong questions then.
Okay, well, we'll do them now so you can just change your answers or write them in there. Letter B, 78.21. There's no zeros in there, they all count. So this is just going to be 4. Letter C, 7.05. That 0 is bracketed in by 2 other significant numbers. So the 7 and the 5 count, the 0 does 2. So that's 3. Letter D, 5.40. That 0 is just like this one. It's telling us it's measured to the hundredths place. So it's significant. So that's 3 significant digits. Letter E, 0.033. These first 2 zeros show you where the decimal point is. So they don't count, just the 3's do. That's 2 significant digits. Letter F, 225, is just like letter B. There's no zeros in it. So 225 is going to be 3. Letter G is just like E. The zeros are showing you where the decimal point is. So only the 1 counts. So that's 1 significant digit. And then letter H, the first 0 doesn't count. The second 0 is telling us it's measured to the thousandths place. So it's important. So that's 3 significant digits. Then on number 8, and I think it was like this on yours too. They've got some answers written out here to the side, but this doesn't answer the question. Okay, it actually is telling you how many significant digits you round it to. So don't pay attention to those. So on letter A, where am I? On letter A, we're just going to do the math and we're going to round it to the correct number of digits. So it's 125 divided by 23.7. You have 3 significant digits here, 3 here. Our rule is to round the answer to the measurement with the least number of significant digits. They both have 3, so we're round to 3 digits. If this is what we get, we would call this 5.27. Okay? So A is 5.27, whatever the units are. They didn't give us units. On letter B, 20.5 divided by 51.0 gives you that. 20.5 has 3 digits. 51.0 also has 3 digits. So we're going to round to 3. We're going to call it 0.40, and it's closer to 2 than it is 1. So 0.402 is the answer to that one. And this 0 does count because it's bracketed in. On letter C, 0.0065 divided by 32.5 gives you that. Now 0.0065 only has 2 digits. These first 2 zeros don't count. This one has 3, but it doesn't matter. So we're going to round it to 2 digits. Now the problem is, well, let's talk about why these zeros don't count. If they did, if we were to round this to 2 digits, we'd call it 0.0, and that tells us absolutely nothing. And anytime we had a really small number, we'd round it off and we would round to 0. That's why they don't count. But if we only count the 2 here, as far as the calculation go, this only gives us 1 digit. So the way we would write this to 2 digits is we would call it 0.00020. So we just add a 0 at the end because this 0 is now significant, even though the first ones aren't, because it's after a number, after a decimal point. Letter D, 1.23 divided by 0.72 gives you that. The 0.72 only has 2 significant digits, so we're going to round this to 2 and we'll just call it 1.7. On E through H, these are just multiplication, so it's the same thing. We're just going to multiply them. 4.72 has 3, 0.52 has 2. So 4.72 times 0.52 gives us that number. If we round that to 2 digits, it's closer to 2.5 than it is 2.4. So we'll call it 2.5. Letter F, 6.3 times 10.08 is that. The 6.3 only has 2 digits. So that's closer to 64 than it is 65. So we're going to call it 64. Letter G, now we're multiplying 3 numbers together. It still doesn't matter. So 1.55 times 2.61 times 5.3. So these 2 numbers all have 3. Both of them have 3. This one only has 2. So we're going to round this to 2 and we'll just call it 21. It's closer to 21 than it is 22. And letter H, we've got a bunch of zeros. So 3.01 times 5.00 times 25.62 gives us that number. This is 3 significant digits. This is 3. This is 4. So we're rounding to 3. That would be the least. So this is closer to 386 than it is 385. So the answer there would be 386. On number 10, this is kind of the why of why we use significant digits and why we round it the way that we do. So let's look at number 10 real quick. We didn't do 9. Yeah, you weren't supposed to do 9. But 9 is the same as number 10, really. We just skipped it. So 10 says, suppose that a pebble has a mass of 12.36 grams and a volume of 4.7. With a calculator, determine the density of the pebble and report all the digits on the display. So the way we're going to find density, try to put that on there so you can see it, is this equation. M is equal to V times D. So in letter A, our mass is 12.36. The volume is 4.7. How do you get the 4.7 on the other side? Divide it. So divide both sides by 4.7. cancel out on that side. I'm gonna solve it. We're gonna write all the digits is what they ask us to do. So 12.36 divided by 4.7 gives us this. So 2.629787.234 grams per cubic centimeter. Make sure you have the work down for this too, don't just have the answer. Then on B, there's actually a misprint here. It says suppose the measurements could be off by plus or minus 0.01. So this could be as high as 12.37, as low as 12.35. And a volume of plus or minus 0.01. That should be plus or minus 0.1 instead of 0.01 because the last digit is uncertain. So this could be as high as 4.8, as low as 4.6. Report the least and greatest values of the density of the pebble. So we're going to put an L here for least and then a G down here for greatest. So the least value is going to be the lowest mass, which would be 12.35 grams, divided by the highest volume, which is 4.8. So we'll divide both sides by 4.8. And let's see what we get for the density, and we'll report all the digits again. So 12.35 divided by 4.8 is this number. 2.5729166667 grams per cubic centimeter. So that's the lowest possible value for the density. The greatest is going to be the highest mass, so 12.37, divided by the smallest volume, which is 4.6. Do the same thing. 4.6 divided by both sides. And we're going to write all the digits. 12.37 divided by 4.6. 2.689130.435 grams per cubic centimeter. So letter C, which of the digits calculated in part B are the same as those calculated in part A? Let's just start at the beginning. The 2 is the same in all 3 of them, right? Is there a 6 in all 3 of them? No. So we're going to put on number, or letter C,